Good evening, everyone, and welcome back to our lecture series during Astronomy Week. It is the third day, and today we are fortunate to have Professor Avinash Deshpande here to deliver a lecture on pulsars. Professor Avinash Deshpande is an astrophysicist and a professor of physics at Raman Research Institute. He is known for his research on astrophysics. He has contributed towards the studies of pulsar magnetospheric emission regions and the elucidation of unphysically ultra-dense neutral hydrogen irregularities in the interstellar space. He is credited with the development of a receiver for high-time resolution studies of pulsars at low radio frequencies. He has been awarded by the Shanti Swaroop Bhatnagar Prize for Science and Technology, one of the highest Indian science awards, for his contributions to physical sciences in 2002. We all welcome you here today, sir.
Thank you for the kind invitation and the introduction. It's a pleasure to talk about and share the excitement about these fascinating objects called pulsars. I realized that there was a talk this morning in your festival about neutron stars and black holes, I presume. And so that has made my job easy. I will assume that you have heard that talk, and there will be some references to neutron stars for which the background is already there with you. These are not the pulsars that I'm going to talk about today, which are familiar objects around us, which you might have seen or even used at times. Although I put together this slide for when I was talking to school children, I realize the relevance of it is actually deeper because pulsars that we're going to talk about today actually represent all-in-one gadget. They involve rotation, dynamo action, energy storage and conversion, space motion, acceleration, braking, sparking, revolving, emission, radiation, and of course, timekeeping. We have been spying on these objects for the last 50 years, and the primary axis along which we have information from them is the time axis. And we have been able to decipher lots of things about them, but a lot remains ununderstood even today after 50 years. Of course, the story started when Jocelyn Bell then, in 1967, when she was a graduate student at Cambridge Radio Telescope. She was trying to use this telescope to study twinkling of stars. By stars, I mean distant objects here, which looked like to decipher the angular sizes of various distant objects by studying twinkling in the radio. And of course, this twinkling was not produced by atmosphere like in optical. This was going to be produced by the interplanetary medium, the medium between within our solar system. And what she noticed was blips of light repeating at regular intervals, which are shown here. Intensity actually increases downward here. The particular chart has been shown to make sure that the writing is seen in the correct orientation. So you had increased intensity present to us, actually these objects, discovering these objects against all the odds, because this required very, very careful observation and follow up before establishing that these are indeed astronomical objects. In this discovery, there is an important message which is tied up with this aspect of what parameter space one was beginning to explore in the process of studying the interplanetary scintillation. Traditionally, radio astronomers were used to taking long exposure measurements. That means they would keep integration times long enough to improve their sensitivity of of or ability to detect weak signals. But here, the variations were going to be fast enough at sub-second level. And for the first, the response time of the receivers, radio receivers, was turned down to make it respond to faster variations. And it was richly rewarded with this discovery, where the signals which existed all along were not visible with the kind of receiver settings one had earlier. And so as one opens unexplored parameter space, there are surprises waiting. And this is one classic example of it. Of course, the initial excitement was to see if these were man-made or they were from some spacecraft, or signals sent to us by some extraterrestrial civilization. This had its own charm in terms of speculations. And as more and more of these objects got discovered, it became clear that one is looking at a new class of astronomical objects, which are, as we believe now, highly magnetized, fast-rotating neutron stars. About these objects you heard in the morning talk. And of course, the original paper announcing this discovery was published by Avinash et al. In 1968. This was after 6 months of secrecy, where people were trying to figure out what these signals are. And I will not go into the controversy, but Jocelyn's supervisor, Avinash, was subsequently given the Nobel Prize for this discovery. What is remarkable about this discovery is how one arrived at, among all possible objects that could be the candidate sources for this, how one zeroed on to neutron stars as potential sources of this emission. It followed very simple arguments. Each one of them gave clarifying clues. Of course, early on itself, Jocelyn Bell ensured to clarify this aspect, whether these signals were following sidereal clock or solar clock. And because we know that the solar time and sidereal time differ from each other by 4 minutes a day, and basically a day in a year. So once it was established, one could call it a parallax measurement in a way that one knew that these objects have to be much, much farther than the solar system. One also looked at the duration of this emission, which appeared in narrow pulses of few tens of millisecond width. And by using simple light travel time argument, essentially saying that the source must be smaller than the speed of light times the pulse width. Because if it were to be bigger, the pulse width of the source. One also thought of whether these were pulsating stars. One knew about Cepheid variables, and in which the period is proportional to 1 upon the square root of the density of the star. Of course, one had already seen enough variety in the pulse periods, and that would imply, if these were indeed pulsating stars, imply a wide variety or wide range in densities. And such a large is for a single class of object is quite unlikely. And so one ruled out that possibility. And one also looked at what kind of rate of energy loss was occurring. And that would amount to the energy being taken out of the rotational energy and rotational kinetic energy of the star. If that were to be so, what kind of energy reservoir that has to be there? And so one found out that the period was changing, but changing very slowly. It was changing sort of a femtosecond per second at that rate, which meant that the energy loss, that we can measure by knowing the radiation that we receive and knowing how much distance it has traveled, we can estimate, we know what fraction that is of the total energy. And this basically suggested that we are looking at a big flywheel, a massive compact object. Okay. And that ruled out, now you have a small object and a very massive object, and for which only two objects really qualified: white dwarfs and neutron stars. We are looking at an astrophysical origin. Among the two possibilities of objects, namely white dwarfs and neutron stars, white dwarfs lost out quickly after the discovery of the Crab pulsar, a pulsar in the Crab nebula, which was rotating about 30 times a second. And given that rotation speed, we can easily see that white dwarfs will be centrifugally unstable. They will blow themselves apart centrifugally if they try to rotate that fast. And so it was clear by Bardeen birth of a neutron star. And of course, we know that they were discovered accidentally later by Bell and Yevich as radio pulsars. In this talk, I will be focusing on rotation-powered pulsars. That means the energy source is the rotational kinetic energy. Of course, their cousins are there, which are powered by different processes, magnetars, which are processed by the magnetic field energies or magnetic energies, and X-ray binaries, which are powered by accretion. This is the famous discovery pictures of Crab pulsar, where 33 frames can be seen, where in each one of these panels, exposure time is 1 millisecond. And you will see there is one object here which appears in some frames, stays there for a while and disappears and reappears again and disappears. And this is the object in the nebula called Crab Nebula, which is also known as M1. It was this, these are optical pictures, but similar behavior is seen in radio as well in terms of appearance of a pulse twice during a rotation cycle. The important thing about Crab pulsar was that the supernova was actually documented. Any further discussion on neutron stars per se, we can come back to it if there are any questions, except to say that the stars that lead to birth of neutron stars originally need to be as massive as 7 times the sun up to almost 20 times the sun. And of course, they go through different evolution, and at the explosion, they leave behind a remnant of the mass close to the Chandrasekhar limit, about 1.4 solar masses. And you've seen this slide in the talk this morning, and also how dense this matter is. The amount of energy released in these explosions is enormous. This is equivalent to popularly stated 10 to the 34 ton bomb. What happens is the core of the star, which is no longer burning anything, which is only cooling, collapses, and the implosion releases gravitational potential energy, which throws away the ejecta, the envelope, the outer envelope, and ejects it at very high speeds. And that's the spectacular supernova remnant you see. And at the center, you have a compact remnant, which has imploded. People had always used this argument of size reduction and the consequence of it for the angular momentum conservation as well as magnetic flux conservation. And so one initially, when one estimated the magnetic fields of the stars, as which are operating as pulsars, one got numbers like 10 to the 12 Gauss and so on, and which was understood as amplification by 10 orders of magnitude of the original field, which might have been, let's say, 100 Gauss. And because of the size reduction and flux conservation, you got this high value on the surface of the star. Similarly, the ballerina effect like situation was considered in terms of conservation of angular momentum to understand the fast rotation speeds of the star. Although one later realized that this is not so easy, because the original spins before the explosion and the magnetic fields of the pre-explosion configurations may not be as high as believed. As far as spin is concerned, one needed to explain now how pulsars can be born with such high spin rate. There was also another problem